So I would want to look at this test here, which is the dependent sample test. It has many names. It can be called a dependent sample test, or by the name before and after tests. Before and after is the most popular name in agriculture because the origin of this test was really in agriculture. Then it found wide use in other disciplines or other sectors where then they were the effectiveness of fertilizer. And of course, this is how this test came about. Then, of course, with revision over time. But it has other names, before and after, dependent sample, paired t-test, paired sample test, repeated sample test, within subjects test, with many names, within subjects, that is medical people, in the area of health, within samples. But it's the same test. Now, this is essentially is one sample. One sample. Pick a sample. I'll give you an example. Probably a drug company wishes to test the effectiveness of a new drug. They want to test the effectiveness of a new drug. So they'll take subjects. Probably they take 8 subjects for testing for the effectiveness of the drug. Then they take their blood samples. If this is for, let's say, blood samples of the hypertension or whatever of the users before they take the drug. Then they give them drug. Then over time, after some period of time, scientifically determined, they collect the samples of blood from the same people. So essentially, this is one sample. One sample. These are 8 people, but 2 pairs of data. That's why it's sometimes called a paired test. In business, also, it has been used. Very many interventions, even in the banks. If the feedback from the customers indicate that the tellers are taking too long at service, or the customers are taking too long at service, meaning that the tellers are slower. So that's the feedback they're giving the bank. Then suppose the bank has say 20 tellers. Then they take a sample of say 8 tellers with only one objective: to test whether an intervention that they will institute would be effective. So the bank can intervene in many ways. They can intervene by training or by training all staff. They can also intervene by giving them an IT application. So suppose they pick these 8 fellas, then they collect their service time. So of course, which is now available actually in the bank data. That's not available this is available. So they collect data on service times by each service time, each teller service time before the intervention. Then they train, that's after training everybody. Before training everybody, just pick a sample of 8, say, if that's representative, then they take their service times. Then after the training, suppose the intervention was training, again, they pick service times to check whether the training is effective. If the training is effective, then the average service time after should be less than the average service time before. That's the assumption. The average service time after should be less than the average service time before, if it is effective. If it is not, then of course the converse is. So that's the before and after, and many, many more examples. You can raise your own examples among others. Even rating, marketers, in rating, Marketers normally use Likert scales. So you probably want to rate, some product in the marketplace, but using a sample of users. So the rating of one, let's say rating 1 to 5, whether it is appealing or not appealing, etc. Then after a while, again, after use, that's before use. After use again, you rate again. Before and after test. Now this, therefore, is a very important test for business students. So this just illustrates you grammatically, visually, the difference between independent samples and dependent samples. In independent samples, the sample sizes need not be the same. On the left, I have 5 people on the left, and I have, say, 8 people on the right. Yeah. In this case, these are independent samples, like testing. This could be male data. In this class, this could be female data. Of course, the numbers are the same. Then testing for difference. This is what we did last time. This is basically the same population, the same sample. Where you have this sample here. This is before, take service time before in the bank, and after, service time after. And then, of course, among other things. Then, of course, some examples here. Classify each pair of samples as independent or dependent. Sample 1, the weight of 24 students in first grade class, and the height of 24 students in the same class. That is dependent sample. These are the same students with 2 pairs of data, with the weight and height. The next example is the independent one. The price, the average price of 15 new trucks and the average price of 20 new sedans. Those are different populations, from different populations, trucks population and sedans population, among others. So now, how do we do this test? I want to, how do we do the procedure? The procedure is the same. What we did last time is what we do here. You define the problem. In words, you define the problem in words. In research, that's what is called a statement of the problem. You state clearly the problem, understand. Probably let's take a case here. We don't worry about this, so I'm going to take you through, step by step. Let's take a case here where you have this is a bank issue. So a bank has the example I gave you, customers are complaining that they're taking too long at service. And then, of course, and then the bank decides to intervene and then takes them for training. Everybody then picks the sample before and the same sample after to test whether the intervention they're instituting is effective. That is step 1, like we did last time. Step 2 is to state the hypothesis. That was step 2, the last time. You state the hypothesis that you are going to test that problem. So the hypothesis, I told you the hypothesis is stated based on a population parameter. Here we are talking, let's talk about the average. This is the difference between means. So it's the population mean. So the hypothesis here will be, and now you have to actually write this. Let mu A, mu subscript A. Now you know what I'm talking about. Let mu A be the service time after, and mu B be the service time before. Anybody have a problem writing that? Let mu A be the service time.
Please say that again.
Pardon?
Please say that again.
I'm saying anybody have a problem writing mu A and mu B?
No, please repeat the statement. Let mu A be service time.
I'm saying mu A be the average service time after, and mu B be the average service time before. You are doing that so that you write a hypothesis. And you know the A and B are subscripts. Therefore, our hypothesis will be, because here we are testing for the effectiveness of an intervention. So H0 full colon, that's the null hypothesis. H0 full colon, mu A equals to mu B. The same thing. mu A equals to mu B. You state it from a position of neutrality. Against HA, then on the alternative hypothesis, mu A less than mu B. Because if it is for it to be effective, so the problem was that they're taking too long at service. So mu A is greater than mu B. That was the problem, that they're taking too long at service, meaning the average after is greater than the average before. Then now, this is where the difference comes in. Let mu D, D, small d, with D subscript, let mu D be the difference between the means. Let mu D be the difference between the means. Mu D. But you know, like they're now writing mu here with waste a lot of time. Let mu D be the differences between the means. So I want to ask you a question to check whether what you are writing is correct. What is mu D when the null hypothesis is true? What is mu D when the null hypothesis is true? What's the null hypothesis? Which null hypothesis have you written?
Prof, I think mu D will be 0.
0.
Beautiful. So when the null hypothesis is true, mu D equals to 0 because it is mu A minus mu B. But mu A is equal to mu B under the null. So mu D, right? That's it. Mu D equals to 0. That's question 1. So to note that under the dependent sample test, which we're doing now, the null and alternative hypothesis, are written in terms of mu D. You write in terms of mu D as follows. H naught, let's write the null and the alternative. H naught, mu D, H naught full colon anyway, mu D equals to 0. Because mu A minus mu B is equal to 0. Mu D is equal to 0. Then HA full colon, the alternative. What is the form of the alternative? Somebody. What will be the form of the alternative? Somebody. Just try. What's the form of the alternative? The alternative now is that mu A is greater than mu B. So let's bring mu B to the right, to the left. Therefore, mu A minus mu B is greater than 0. Mu A minus mu B is greater than 0. If you just bring mu B to the right, under the left, under the alternative, then mu A minus mu B is greater than 0. So the alternative in this respect, therefore, the hypothesis will be like this. H naught mu D is equal to 0. HA full colon mu D greater than 0. So that is the form that the hypotheses are written under the dependent sample test. You undertake any such test. That is the form you write. As long as it's a test of differences between the means. It could be difference between the modes, difference between the medians, whatever. So that is step 2, writing the hypothesis. You state your 2 hypotheses, the alternative and the null. That was step 2. Step 3. State the test statistic. to test the hypothesis designed into above. You state the test statistic to test the hypothesis designed into above. That the mu A is greater than the mu sorry, you test the hypothesis that the service times were longer. Of course, that's the hypothesis designed into above. So then, so what is the test statistic here? There's the things I'm going to tell you, not even bother being cramming here. That's why I want to go through it. But the test statistic here is really easy. This is normally, if the sample is large, then you use the Z test. If the sample is small, then you use the small test, the T test, just like we did last time. So let's take, because the procedure is the same, I want to take a smaller sample so that it is easier to manipulate. You know, of course, again, we're doing this online. We don't want to go to large data sets. Let's take the T test, the T test, a small sample. So the sample, the test statistic under the T test is, for about this, I'll show you how to deal with this one here without even bother. The test statistic is this one. So write that. T is equal to this one. T is equal to d bar minus mu d over SD divided by the square root of n. This one, this is the most important one, this one. T is equal to d bar minus mu d over SD divided by the square root of n, where SD is the standard deviation of the differences. Standard deviation of the differences. D bar is the arithmetic mean of the differences. The arithmetic mean of the differences. And of course, mu d, I'll tell you what mu d is. N is the sample size. Probably you take 8 tellers. And of course, mu d is the population mean of the differences. The population mean of the differences. However, T is calculated assuming the null hypothesis is true. You calculate T assuming the null hypothesis is true. And when the null hypothesis is true, then mu d is equal to 0. So essentially, therefore, T will just be d bar minus 0 over SD divided by the square root of n, with n minus 1 degrees of freedom. N minus 1 degrees of freedom. So this is what I want us to calculate. Forget about the formula up there. This is the most important thing here, really. The t-test statistic. The t-test statistic. So I'm going to go and generate data in Excel, and this data relates to the bank problem of testing for the effectiveness of an intervention. Effectiveness of an intervention. So this is my data. The data here is this are teller. These are tellers. Tellers. And of course, tellers are 8. So it's 1, 2, 3, 4, 5, 6, 7, 8. 8 tellers. And this is the service time before X before. That B there is a subscript. X is the service time before. The service time before. The time they take serving customers before that intervention. The service time before. Then the next column is the service time after. XA. So this is the service time before, and then you have here service time after. Service time after. So what are the service times here? Let's just take small, I mean, any data here. 5 minutes, say 8 minutes, 4 minutes, 7 minutes, 6 minutes, 9 minutes, say, and then I'll say 2 minutes and say 10 minutes before training. That's how long these tellers were taking to serve the customers before the intervention. Then after, this is 6. Of course, it does not mean that when you train them, their service time all will come down. Some of them will even be serving at 12. Some of them will come to 3. This one probably is 5. This one probably is still 6. This one probably is, say, just 8. And this one, say, is 4. And that one, say, is 7. Those are service times after. You are collecting this data to test for the effectiveness of an intervention. The effectiveness of an intervention. Effectiveness of intervention. There's something I'm going to change it a bit. Just go to result anywhere. So now, how do we do this? First of all, here, you want to calculate this. This is what you want to calculate. That's why you are collecting this data. So I get D, the differences between them. D, it does not matter what you subtract from what, just get D. So D is say this one here minus this one there. That's the first difference. And for all the differences, for all the tellers, that is the difference between the means. For all the tellers. Now, based on this, you get sigma D. Write down here sigma D. Sigma D. Sigma D, because you want to get D bar. Sigma D is here. You must write down there sigma D. Here is equal to -1. Sigma D is equal to -1 minus 1. Therefore, we get D bar. So you must write D with a bar on top. D bar, I'll just write mean here. Mean. D bar, which is here up here. This one here is equal to minus this, that, divided by 8. There are 8 tellers. 8. That is the average service time. Of course, it is not 0. I know because we have decimal places. I'll increase this so that you see 2 decimal places, so that you don't give you a misleading result. Even 3. So that's D bar. Minus 1.25. Even for this average alone, you can crudely say that you know, the effective, talk about effectiveness just by looking at this, but that's no testing. Then we get SD. SD is the standard deviation, which is just D minus D bar minus 1.25, minus 1 that is a D bar. So it is plus, because it's minus, I'll just add here. Minus, or I just write minus mean, but you write minus D bar, minus mean. Or you write minus D bar. So then square them. Square, because we want to get the standard deviation. So essentially, this is what it is. It is this one. It is D. Where is D? D is here. Minus, so it is plus. So there's a plus there. Minus 0.125. Bracket, whole squared. That is the first one. So I can also make this to 2 decimal places for ease of reference. Then I do it for all. Those are the squared differences. The squared differences. Then we sum them. We sum them. That is the sum of the squared deviation. So that is so then we get the value. You must write S squared D. S squared, because this we want to get the variance. The variance is this SD squared. Just like S squared D, the variance of the differences. S squared D. So me, I'll write here variance of D. Variance of D. Variance of D is essentially this one here, because we have no frequencies here, divided by 8. That's the variance. Therefore, SD. SD, which is this one here, you must write the subscript. SD is the square root of the variance. Square root of the variance is here. That's the square root of the variance. which is this one here, to the power of 0.5, which is 2.2. That is SD. SD. But we know N. N is 8. We know mu D at when the null hypothesis is true. So mu D essentially is 0. So all we need to do here is to substitute, therefore, T equal to minus 0.125 minus 0.125 divided by 2.2 over the square root of 8 divided by 2.2 over the square root of 8, which essentially means I would just deal with here. I'll calculate it for you quickly. So what is this? The square root of 8. The square root of 8. That's the square root of 8. Of course, that's not exact. So I take that square root of 8 up. I'll do it quickly for you here. But you can also do it on your calculator. Times this one here. Divided by SD. Where is SD? That is SD. So that is our T. Our T is this one. You need to check that you've gotten the same. Eh? Our T is this one. What is not 0? That's our T. Yeah, minus 0.160. Minus 0.160. That is your calculated T. T calculated, this one. This one here. That is step 3. Then step 4. You select your level of significance, alpha. Select the level of significance, alpha. Select the level of significance, alpha. In this case, let alpha be 10%. So alpha is 0.1. I hope you're writing alpha the letter, the Greek letter. Alpha is 10%. So therefore alpha is 0.1. Because until you choose any alpha you want. So note that. Given the nature of the alternative hypothesis, given the nature of the alternative hypothesis, in this case, mu A greater than mu B. Mu A greater than mu B, even if it's less than mu B. This is a one-sided test or a one-tailed test because of the nature of the alternative hypothesis, greater than, even if it was less than, that's fine. Hence, from the T table, read, don't write this until I finish it. T, 0.1, that's the level of significance, 0.1, comma, and I told you that this is governed by with n minus 1 degrees of freedom. N here is 8, 7 degrees of freedom. So you read from the T table. That's what you read from your T table. The T table. Of course, these are subscripted. So you go to your T table and read this. T 0.1, 7 degrees of freedom. So if I go to T table, our T table. Our T table is here. This is our T table. It's a one-tailed test. So we use this row here. We use this row, we go all the way up to 10%. 0.1. 0.1 is here. 10% is here. We go down to 7 degrees of freedom, which is here. The T value there is the one intersecting, which is 1.4, this one. That's our T table value. That's our T table value. Our T table value. our t table value, which is 1.45, 1.4415. Our t table value is that. So you'll get that from the t table. Next, step 5. Compare the t calculated equal to minus 0.160 minus 0.160 with the t table value, which is 1.415. And given that the t calculated is less than the t table value, it is less, it's negative. The t calculated is less than the t table value, then
We accept.
accept the null, meaning that the training was not effective. That's why I wanted to come and check, where I told you, where you are deciding your hypothesis, just go back there, where you're deciding your hypothesis. We said mu A was equal to mu B, and mu A was greater than mu B. That's true? So you change that greater than to less than, because you are testing for effectiveness. Change that less than to greater than to less than. To less than. Everywhere, even mu D should be less than 0. Because you are testing for effectiveness. If it is effective, then the after should be less than before. So then you draw your conclusion here that the training was not effective. If it were effective, you would have rejected the null and accepted the alternative, where mu A is less than mu B. So that is this test. It's a simple test, but a very popular test, which used widely. So I've given you the procedure. That procedure is what you follow. If you go here, you will see some formulae. Forget about those formulae. What about them? Just follow the procedure I've given you. You know how to get, this was a reading center claims that students will perform better on a standardized reading test after going through a reading course. They'll perform better after going through a reading course. So what you do, you get the test before. Then you get the test after the course, based on a sample of 6 students. Then test for the effectiveness all the way, and they're here. Forget about this formula here. This is just calculating the standard deviation. You don't need this. Just use the procedure I've used. The procedure I have used to get the standard deviation. And of course, that is the dependent sample test. That dependent sample test. Any question, please?
Yeah, Prof, could you just go back to the Excel sheet?
Excel,
Yeah.
Excel sheet. Excel is there.
The 2.8 and the negative 0.1, negative 0.16 are, I lost you there.
No. I want to, you know what I was doing here? You know what I was doing here? I wanted to check whether you've gotten the same result for this one. I didn't want to do it here.
Yes, I've gotten the same result. But that's 2.8. I got up to the SD 2.2. So I wanted to know how to apply that on the formula. The
no, you substitute. What is DIBA?
Yeah,
you're
that's
not
what
using
I
Excel, What's DIBA?
DIBA.
I hope you're not using Excel extension.
Negative 0.125.
Negative 0.125 minus 0. Are you see where I'm pointing here?
Yes.
I want you to substitute that into that formula, then calculate.
Yes, I've done that. Then SD is 2.2.
Yes.
Minus square root of 8.
Is it minus or divided by?
Over.
Divide by.
Divide by. Okay, over square root of 8. Then I've got it. Thank you.
So you got your value, but you got the same value.
I'm calculating now.
That's all. Then that's fine. So now that is the test. which I'll repeat is a very important test. So you can test this test appropriate for where you have the ratios type of measurement, ordinal, ratio and ordinal. You can even test for change in perception. Change in perception, by rating, Likert scale. You can use this test to look at if there's some change in perception. Even in voting. People use this test. Even you basically just pick a sample, and then of course you can look at the likelihood of voting. You can rate them before a campaign period, and then a likelihood of after a campaign period, effectiveness of that campaign intervention. If that is what you want, that's where marketers use this in promotion campaigns. They use this test quite a bit. So now let's go to the next.
Excuse me, sir.
Which is the final test of hypothesis.
Me,
and these are called non-parametric tests. There are a number of them.
There's a question.
Yes, please.
Yeah, excuse me, sir. Sorry for the interruption. I just wanted, could you kindly
Not clear.
I'm saying, could you kindly just remind me how to get the 0.1 and 7? Just this read me.
Oh, I get what?
0.1, the T 0.1.
No. I want you to do this thing. I want this I'm repeating. Minus 0.16, eh?
No, the T 0.1 is the 10%.
Which one? Which one is that?
0.1. The T 0.1.
This
The
one.
level of significance.
Yeah.
No, the level of significance.
What did I say about level of significance?
You said we take
You
10%.
You select. The step is we select.
That's your own.
Yeah.
Yeah.
You
Oh,
select.
But, for a particular data, and this is really, that's a good question, though. For this business statistics, but if I want to show you how to get an appropriate level of significance, then now we are going mathematical. That's what I'm saying, select. And I also said last time, the most commonly used level of significance in business research is 5%. All business processes is 5%. But I was trying to show you here that you cannot still use another level of significance. And I also told you last time that in the area of health, the level of significance should be very small, probably just 1%, because the level of significance is the probability of rejecting a true null hypothesis, the producer's risk, and it becomes a very serious matter in those pure sciences, engineers, architects, when they are drawing, the allowable threshold, very minimal. So for you, just use 5%. But I'm telling you here that you can use others. That's what I'm trying to say. So now, we went to the parametric.
I have another question, sir.
Yes,
Sorry.
please.
What was our hypothesis, kindly? Because you're saying we reverse the greater than and the less than after
Yes.
our calculated T.
Not after. I said that I would tell you what to change later when I'm done. When I'm done.
Okay.
But your hypothesis should let me tell you, but still alongside,
Yeah.
the issue here is that you are testing for effectiveness of an intervention.
Yes.
Which means if you're using service time and if the intervention is effective, if you're testing for effectiveness, then the mean after should be less than the mean time before. That's true, isn't it?
Yes.
Yeah, so that's why I was thinking reverse. There's just a
Yeah.
small error there, really, which I think, but you do it at that step. You are testing
Okay.
for it. Yeah, that's fine. So now let's go to this test here, which are parametrics. So now what's a parametric? Non-parametric. I mentioned this last time. Of course, these are not driven by probability distributions, the T, the Z. These are distribution-free tests. In fact, they are driven, but they are based on the frequency distribution table. But these tests are only used when the scales of measurement are either nominal, ordinal, or interval. Nominal, ordinal, or interval. And they have many applications. Many. You probably want to test. There's a claim out there. There's a claim out there that the area of specialization of an MBA student affects their performance in, say, statistics. So we know I can pick your areas of specialization. Then I look at your performance in statistics in terms of the grades. These are frequencies. How many people in finance got A? How many people in finance got B, C, D? So testing, you are trying to test whether your level of specialization affects performance, or gender affects performance. Again, this test has a wide application in business. And I know most in your research, you use this test. I'm aware. You use this test because of the nature of the data you collect. It is one of the tests you will use in research. Now, there are a number of non-parametric tests, but I'll only deal with the one, which is the most commonly used in business research, and that is called the chi-square test. The chi-square test. Chi is a Greek letter. I'll just give you chi here in a minute. The chi-square test is a Greek letter. A Greek letter.
We can't see us.
Well, like this. So chi-square, chi. That's Greek letter chi. But this is the word chi. But that's not the symbol for chi. So this is a chi-square test. Before I go to chi-square test, forget about what I've written here. I just want to go here. These flowcharts I've given you here are all the possible statistical tests you can never undertake in life. All of them are here. We have done this one. Where is that one? We have done we are on the right-hand side. On the right-hand side, where are we? Not on the right-hand side. Where are we? Yes. Good. Where is it for independent? 2 or more. We see where we have done correlation, regression. Good. In the middle. I'm in the middle here. In the middle. Differences between means. These are the possible tests. They are here. Independent, dependent, which are called related. And we have only done for parametrics, this one. And we have used this one. Independent one, we also just use this for parametric. And we have used this. Of course, I told you there are many, but these are the non-parametric side, which I'm not going to bother about. This is where I was, and I've done all this. Then now we are here. These are comparing frequency tables. These are the non-parametric tests also. Here, we are only focused on the left here, between observed samples, the chi-squares. Sorry. Here, for independence, between 2 samples. Here, that's where we are. So here we'll only do this. Then come down, the chi-square test, here. The rest are the other many, which I've told you we are not bothered about. So this flowchart, keep it. So if somebody asks you to do a test, you want to look at the data you have, you got just check which is the appropriate test here in future. So chi-square test is meant to achieve the 2 objectives. It can either be used to test for what is called the goodness of fit test. Whenever you are doing research and you're collecting data, we make sweeping statements that when n is large, then the distribution is normal. And when n is small, the distribution is t. How do you confirm that is actually normal when n is large? And that is t when n is small? We use the chi-square test. That's why it's called goodness of fit test. Fitting your data into a distribution and then checking whether it actually fits the data. That is not here. But I'll give you information about this, so that in future when you are reading them, your home and dry. You can always check. What about that one? What about that? Or it is meant to achieve this. This is the symbol for chi-square. That's not an X. That's the symbol for chi-square. Chi-squared test of independence. And that's the focus of this course, of this topic. Chi-squared test of independence. And I've said this test, you can only use it when your distribution is either nominal, like gender, area of specialization of students, or ordinal, Likert scale ratings, or interval grouped data. You can only use it for those three, when those three are in place. So if you want to use chi-square, but you have collected quantitative data, you must group them for you to subject them to this test. Otherwise, the test will be meaningless. So I'm going to give you the procedure. The same procedure we have followed is what we are following here. The same. There is no difference. So what is the problem here? So I'll give you the problem. Let's just take the problem I've just talked about. That there's a claim that area of specialization affects student performance in statistics. That is what is apparent to the School of Business, that your area of specialization affects your performance in statistics. That's what they're suspecting. Then but they cannot take that as gospel truth. They must really check whether area of specialization affects performance in statistics. So they decide we are going to use chi-square test. To use chi-square test, we must ensure that area of specialization is either nominal, ordinal, or interval. But area of specialization can only be nominal, because could be 1 is equal to finance, 2 is equal to HR. That's nominal. 3 is equal to strategy, 4 is equal to what? Whatever. Then performance in statistics. How are they going to measure performance? They look at the student performance from the past. In statistics, they cannot use GPA because GPA is not per subject. They decide they cannot use either the student grade or the actual marks scored by the student. If they were to use the grades, that is it, because grades are already ordinal. A, B, C, D, that's ordinal. So it satisfies the requirements of chi-square. But if they're using the marks you have actually scored, the marks are numbers, 10%, 30, 40, 90. You must group them to convert them into interval. 0 below 10, 10 to 20, 20 to 30, 30 to 40. Very important. So the first step, therefore, that I've defined the problem, that there seems to be an indication that area of specialization affects performance of the students, given that some area of specialization, they are defining the problem. Then step 2, define the right, and I want you to write this, because that's what the example here. Design the hypothesis. There are two ways of, there are standard ways of writing the hypothesis here. If you're not a business student, chi-square hypotheses are written in terms of probability. But we avoid probability to write those hypotheses in business statistics. So under chi-square, you state your hypothesis in words. You state your hypothesis in words. For example, in this case, right, the following, H naught. H naught is stated from a position of neutrality, that there is no relationship. In fact, right, there is no significant relationship between area of specialization and student performance in statistics. Significant, actually statistically significant, because there may be a relationship, but it is not statistically significant. There is no statistically significant relationship between area of specialization and student performance. That is HO. neutral. Then HA, full colon. There is a statistically significant relationship. Statistically significant relationship between area of specialization and performance in statistics. That's the alternative. You simply state it in words. But in future, as you go and do research, you also have to follow the USIU format of writing hypothesis. They have. When you do research, they will give you. But it's the same spirit, the same thing. Others would have just written H naught, student performance, sorry, area of specialization and student performance are independent. No relationship. HA, student area of specialization and student performance are dependent on each other. But that's a very cruel way of writing a hypothesis. The first way is the closest and the best. Then you follow the same steps, I can tell you. You follow the same steps. Step 3. What is step 3 in hypothesis testing, please? The one you've just done. What was step 3?
You state the test statistic.
You
to
state
test the
the
hypothesis.
test statistic. Now you state the chi-square test statistic. The chi-square test statistic. Which again, we derive ourselves. But for you use it. Use it. And I want you to remember that chi-square is written like this. It's not an X. This one. It's not an X. So what is the chi-square test statistic? I'll give you the chi-square test statistic. The chi-square test statistic, so that you just copy, I don't want to bother many things, is here. Remember, this is not an X. This one. I want you to replace this, change this. This thing here should be chi-square. Let me just get chi-square somewhere. Where is this thing? Can't get it here. I can't get it here. But what I can't get it. What this is Excel. This is PowerPoint. I want to change it for you. But I want you to write this, not X squared. That looks like an X. I want to write this one. This one up here. This one. This is what I want you to have. There. Yeah. The chi-square test statistic. That's good. Copy that. Then I'll define this is a very easy test. Sorry. What have I done now? You take something. The chi-square is equal to sigma. So that is summation. Sigma O minus E squared divided by E. O minus E squared divided by E. There are many ways of writing this, but this is the easiest way. So note this. Just note that. Note that the chi-square test statistic is driven by what are technically referred to as the expected and the observed frequency. Expected E is expected, and the observed frequency O, where the expected frequency, the observed frequency are the actual frequency distributions derived from collected data. Those are the exact, and you'll see it here in a minute. Frequency distributions collected from data. While the expected frequency are those frequencies that are determined assuming the null hypothesis is true. You determine them assuming the null hypothesis is true. And if the null hypothesis is true, this is based on theory, then the observed frequency O should be equal to the expected frequency E. They are supposed to be the same if the null hypothesis is true. They are supposed to be the same if the null hypothesis is true. But of course it can't, because the reality, that is theory. Reality, they'll differ. So it's these differences between O and E that you are testing for. And I'll tell you how you get this in a minute. That's the first one. Note two. Number two. Note that the chi-square test is driven by what are called contingency tables. Contingency tables. Contingency table is just a one-way table. You'll see it in a minute. A two-way table, a one-way table. Contingency table, frequency distribution table, anyway. Contingency tables of observed frequencies and corresponding expected frequencies. Observed frequencies and expected frequencies. Contingency table, that's a technical name of those frequency distribution. And that's now where I want now to move to Excel to show you how you derive an observed frequency contingency table, and then how you derive an expected frequency table to enable you calculate chi-square O minus E squared over the corresponding E. So we go to our Excel, then let's use the problem. Let's pick around 4 areas of specialization in this problem. 4 areas of specialization. Area of specialization, which probably are give me the area of specialization. Let's say there's a minute here. So these are areas of specialization. Specialization. Which space somewhere here. Like that. And here we can talk about strategy. We can talk about HR. We can talk about finance. We talk about marketing. Student performance in statistics. Let's use grades, eh? Let's use grades. A plus. A. A minus. B plus. And B. This one, because I'm using line data, you won't copy this, eh? But you just understand this, eh? How many students taking strategy? I can generate a random number here. Random. I want to give you. These are grades, eh? How many of these students are there? Say. Round. Between. We just generate numbers here. Between, say, 10 and 40. So let's just get the number of students who scored this marks, these grades. Those are the students. You don't have to copy this really. Just because it's a better, even there are examples on your PowerPoint. Just listen to this. Better to know. So these are. Sorry, need to want negatives here. Where is the negative coming from? Where is the negative coming from? Because I put a negative somewhere.
The formula. There is a problem with the formula when you click on the.
But it's okay here. Probably I don't know what I did. Let me just check again. I'm doing this. Test special values. Good. That's what I have. Then you have total. This is the actual data you're collecting. How many students over the past sample, over the past 2 semesters have scored these grades? These are student performance. This is not the way you collect data. You enter the data, then you organize them into a frequency distribution table, which is this one. This is what is called a two-way table, because you only have two variables there anyway, which is the area of specialization and this. So there's a two-way contingency table. But they need to, for it to be fully defined, you need total. How many strategy students were selected? They are here from that sample. How many HR students were selected? They are here. How many students scored an A in that sample? They are here. How many students scored an A minus? They are here. What is the total sample? Total sample is here. So you went to the past and that's what you got. So this is the observed frequency contingency table. I want to make it an easier thing to deal with so that we don't use these funny numbers here. But it doesn't matter. Does it really matter? It doesn't matter. So this is the observed frequency, the actual data you collect. Observed O. Observed frequency O. You understand that table? Okay. Then expected. If the null hypothesis is true, then expected should be the same as observed, like this. But it cannot, I can tell you. It cannot, because in reality, there are many other factors. So this is the expected. How do we get expected from observed? You get expected from observed. I hope you are noting those little things. Expected from observed contingency table. So it means these figures here are inappropriate. You get them from you use the observed to derive the expected. So before I go there, I would want to ask you this too, so that all of us understand what I'm talking about. Which two totals intersect here? Which two totals intersect at 15? Anybody? Which two totals meet at 15?
Strategy students that scored an A.
Which totals? Now I'm talking about totals.
104 and 106.
104 and 106. And here?
103 and
3.
And here? 102 and 106. Here? 60 and 106. Here? 104 and 81. Here? etc. Clear?
yeah.
Good. Now, that's an important aspect. The next one is that you need to note this little thing. These values here have their corresponding values here, meaning that 15 has this corresponding value here. 39 has this corresponding value here. And I told you if the null hypothesis is true, if this is 15, that should be 15. 39, 39, but it cannot. So how do we get the expected for each of these? This is a procedure, very simple procedure. You multiply the intersecting totals. So I come to cell 1 here. I multiply the intersecting totals. What are the intersecting totals here? They are here. 104. I multiply them by 101. 106. Then divide by the grand total. What's the grand total? 360? 369, eh?
369.
So that is the expected frequency. I want to put this in 0 decimal place so that we are okay. That is the expected frequency that corresponds to 15. Expected frequency that corresponds to 15. Where is that thing? Where is that stuff? Here.
Come again, please. Doc.
Just a second. I'm doing other things.
Okay.
I'm doing other things first. I want us to get the actual, because these are people, these are not, these are, cannot have decimal places here. So, when 30. So it means, I said you multiply one of, because you want the expected for 15. You multiply the intersecting totals. This times that, divide by 369. This, and here
Okay.
you want to multiply what?
That would be 103 by 106.
Eh?
And by 369.
Divide by 369 here.
102 times 106 divided by 369.
So you are because I want to use exact right, to do this thing. Eh? So what is a constant here? What's a constant along this row? What's constant along this row? This one.
106.
106. So I'm going to make 106 constant. Where is 106? 106.
Also 369.
F.
F3.
69.
And 369, of course, is a number, isn't it?
Yeah.
So that's it. I've made 106 a constant. Eh? So I can now get the expected for all of these things. They are here. So this one here is this one. This one here is this one. This one here is this one. This one here is this. But critically, these totals must be the same. These totals must be the same as that one. Am I clear, please?
Yeah.
Then I want to do it for all. I want to do it for all. You know what I do? I just kind of make 7 here. Make 7 here a constant. Where's 7? Make 7 a constant. That is row 7. Make row 7 a constant. My job is done. Row 7 a constant. Then you come here. Then I do it for all. So those are our expected frequencies. These totals must be the same as these totals. These ones must be the same as these ones. Am I clear?
Yeah.
Yeah.
Crystal clear.
Next is now based on these two, the expected and the observed. Now you calculate the chi-square test statistic. And I'll give you the easiest way. There's another way I've given you here in your PowerPoint, but the easiest way is here, which to me is the best. But again, you can't do it. You can't do it on your notebook. I know you would say why you cannot copy it now. You know, you can just check what I'm doing. This is what I want to calculate. That is what I want us to calculate. This one, the chi-square test statistic, this one here. So the easiest way to calculate this, you know, this is a summation. It means I'm going to subtract this minus that, I square it, then divide by 30, plus this minus that square, divide by 30, plus this minus that square, divide by 30, 29, then this minus this square, divide by 70, divide by the corresponding expected. So how do I do that? You convert your chi-square test into a table. Because I'm using Excel, I want to make these things constant. Values. So you simply change this relationship here into a table. Get a column here called the O column. Then go to the E column. That expected influence column. Then get the O minus E. O minus E. Minus E column. Correct? O minus E column. Because our statistic requires we get. Then get this one square. That one square is there anyway. Square. So we're wasting time. Square. Then get this one here. Bring it here. Then divide this by E. Divide by the corresponding E. This one. Divide this by the corresponding E. Divide this. I'll just write it here. By corresponding E. So you have divided by the corresponding E. So how do I get this? And look at what I'm doing here. This row corresponds to this row. This row corresponds to this row. Similarly, this corresponds to that until the fourth row. So all I need to do, because I'm using Excel and I want to put this in column form, I bring this one here and I transpose it here. Because I'm using Excel. If you're using just manual, that's what you do anyway. You change those rows into columns, and then you change all of them into columns by just pasting below each. That is the one. Sorry, no, transpose. Then I also transpose this, change them into column. I'm just, sorry, what is that now? Transpose, column, Then I pick the third one again. I just put it below. As long as you're consistent, you'll be okay. You come here and then post that one there. That's what I'm saying. This one you shouldn't even bother writing because of the rows are many. Then I like the last one here is this one. So this thing has only 4 rows and 4 columns. 4 rows and 4 columns. Those are my observed. Then I write the corresponding expected. Corresponding expected is here. Corresponding expected. Now, what do I do? I can't. Corresponding expected code. Then I bring it here so that I can calculate my chi-square test statistics easily. I also do here, come here, and I do here. That corresponds to that, corresponds to this, that one there. Then I come here, here, and I do this, that one there, and then I do that, that, then lastly, this one, that one. And here we are, bring it here, here, and I post. I've converted all my rows into columns corresponding of observed and expected. Then I do what here? I do here what we are saying here is O. What is O? O minus E. It is in the test statistic, whole squared. O minus E whole squared. No, what I've done. O minus E whole squared. I know what I've done. Just a minute. O bracket O minus E. O minus E bracket whole squared. And that's what we get for each of them. Of course, those are many decimal places, doesn't matter. We'll deal with the numbers later. Then divide this by corresponding E. You divide that by corresponding E. That's why using a table is good. By corresponding E. So I've reduced the long summation, which I'll show you here, into just this. Then I sum them. That's what summation is. Sigma is here. Then I sum them. You sum this, which is 32.718. You just write somewhere. Chi-square is equal to 32.718. That is this value here. Is equal to 32.718. 32.718. Step 4, or whichever. Using a level of significance of 5%. Using a level of significance of 5%. And given that the alternative hypothesis is two-tailed, and I'll tell you why it's two-tailed. The alternative hypothesis is two-tailed. Then read from the chi-square table. Read from the chi-square table. I hope you get used to writing chi-square, the symbol. Read from the chi-square table the following. Don't write this until I finish it. Read from the chi-square table. Not just use C, but you use the symbol of chi, not C. Read from the chi-square table. You know, if you're taking a level of significance of 5%, and the alternative is two-tailed, so you're going to use half 5%. Half 5% is 0.025. So you read from the chi-square table. Don't write until I finish. 0.25, comma. Before I finish, don't write anything. C minus 1, bracket, times R minus 1. All of these are subscripts. Subscripted. C minus 1. All these are subscripted. Price it channel. So these are subscripted values, which are here. For me, I've used C here for chi, but you must write chi square. The little symbol, chi square this. Where C are the number of rows in the contingency table, and R the number of columns in the contingency table. How many areas of specialization do you have here? How many do you have? How many areas of specialization do you have?
4.
4. So R is equal to 4. How many grades do you have?
4.
4. So you're going to read, therefore in this case you read this one. What is 4 minus 1? 3. 3 times 3. 3 times 3 is what? 9 degrees of freedom. So that's what you get from the chi-square table. And please write the symbol for chi-square. So this chi-square test is driven by C minus 1, R minus 1 degrees of freedom. Those are the degrees of freedom for chi-square. So what is the chi-square table? I go to chi-square table. I'll give you the table in a minute. We are going to read that from the chi-square table. The chi-square table is like this. This is the chi-square table. Here's one. We shall explain. Up here, the first column is DF. DF are degrees of freedom. So you will go up to 9. Up to 9. The level of significance are the subscripts of chi-squares here. So we have levels of significance here. We are using 0.025. So you go up here and you reach 0.025. It is here. Here. So come 0.025 up to 9. What do we get? Up to 9. Which chi-square is that? Which chi-square value is that? For those who can see?
19.023.
That's the one. This one. This one here. 19.023. So that's 19.023.
023, yeah.
Yes. Where we have it here, I'll come back here, which here is 19.023. That's the chi-square table value. The chi-square table value, which is
Sorry. Can I take you slightly back? How did you get the 9 degrees of freedom? 9?
Anybody?
We multiply the C minus 1, which is 3, and also R minus 1, which is 3, since it's a two-tail.
C
4 minus 1
was 4. Okay, yeah. 4 minus 1. Okay, got it.
That's that. So that is it. That's the type of table value. Then we go to step 5. You compare the chi-square table value with the chi-square calculated. If the chi-square calculated is less than the chi-square table value, you accept the null. The same thing. In this case, the chi-square calculated, which is 32.718, is greater than the chi-square table value, which is 19.023. So we reject the null. We reject the null and conclude that area of specialization actually affects student performance based on the sample data you have used. The area of specialization, there is a relationship. It affects student performance. That's the conclusion you draw from this, because you draw the conclusion based on the problem. Clear?
Come again, please. Sorry. If the calculated is bigger than the one from the table,
you follow the same procedure. You know the same. Since we started testing, there's no difference here. If the chi-square calculated is less than the chi-square table, we reject the null. If it's greater, you reject the null. Then you draw your conclusion based on the problem you define in number 1. But you put it in your own words, not exactly mine, your own words. You know, your own words. You know, as long as you're rejecting, how do you interpret the rejection? That's what's important. How do you interpret the rejection of the null or its acceptance for that matter? But in your own words. So that is chi-square test. That's chi-square test. And then the chi-square test here. I'll go back here. Yeah. So this is what you have done. And so here, this is what you have done. So there's a problem here where somebody wants to check whether where the house is located is influenced by influences the housing style. So you measure the house location as either rural or urban. That is C is equal to 2. The styles are also 2, type 1 and type 2. So you want to test whether where the house is located is where the house is located influences the style. Influences the style. This is what I want you to do in a minute, but we'll come there. Then the other one, yeah. Here. Sorry, I'll go here first. Here. You know, this is the way instead of using a table, which I've used to calculate chi, you would use this, You would this is what you'd use, and it's cumbersome. Subtract expected, observed minus expected, divided by expected, plus this, plus that, plus. Just use the table. This is the same thing I've done up. In this other example here, this is a marketing research problem, where it is assumed, you know, here there's a case where what happens, which soft drink do customers prefer when they go to an outlet? So this marketer is assuming that that consumers of Coke, Diet Coke, has an alternative. That if there is no Diet Coke, they will always take Diet Pepsi. So even if there's no Coke, nobody should worry. So they go to the field and collect data from the youth, from the consumers, and ask them those who consume Diet Coke, Pepsi, and those who consume Diet Coke. You want to check whether there is a relationship. And just ask them simple question, yes or no. 84% say they don't, they consume neither. 84. 32% say they don't consume Diet Coke, but they consume Pepsi. And the other one said, yes, the Diet Coke, yes, 48, but they don't consume Pepsi. Then the other one said, we consume both. So you have to test whether there's a relationship. This data alone does not make sense. Chi-square to test this. And this is the one I want you to do. So I want you to give you a few minutes. This is a very small thing, very small. So determine the expected frequency, which is here. Then determine the chi-square test. But we are going to agree with you here. How many rows are here? How many rows are here?
3.
How many rows are here?
2.
2.
2.
So how many? What are the degrees of freedom here?
0.5.
What are the degrees
0.05.
of freedom?
Oh, 1.
Degree 1.
1, eh?
Why 1?
0.
2 minus
2 minus 1, yes.
2 minus 1 times 2 minus 1. So it's 1 times 1. 1.
You say. To do this, but I'll give you the chi-square table value. I'm giving you the chi-square table value. I'm giving it to you. So it is 0. So we are doing it at 5%,
Yeah.
It's at 5%. So I'm going to go to the chi-square table, and I'll get you that. I'll get you the 5%. The 5% basically is here. 0.05. 5%. 1 degree freedom, 0.5. 0.5, 1%. 1 degree of freedom, So it's the value there is is 3.841. 3.841. That's chi-square table value, eh? 3.841. So my job, I want you to calculate for me, is this. The chi-square calculated. That's what I want. Then you draw a conclusion.
I have a question.
Yes, please.
How come we have already assumed that this one is one-tailed?
You haven't assumed. What is actually, what's the hypothesis here? What's the hypothesis here? What's the hypothesis here? The hypothesis here is that the hypothesis here is that those who could, this actually one-tailed, one-directional, eh? Why one-directional, eh? That those who consume, the problem here was that those who consume, in fact, let me go back. You write the alternative hypothesis based on the problem. The problem. But the problem here, which I was defining, is that those who consume Coke will consume what? Will consume what? Or the likelihood of those who consume Coke will consume what? Pepsi.
Diet Coke.
That Coke. So if you check the note, you read the language of your null, of your alternative. You don't assume. You read. You know, it's you will be writing the hypothesis. You. So just read the language of your hypothesis, the alternative. Then decide, is it one-tailed or two-tailed? So let's go calculate that thing very fast. Then please draw your conclusion. I want you to draw your conclusion, your own, in your own words. In your own words.
You said the table value is?
The table value. Table value, you want the table value is what? 3.8.
3.41.
41, yes. I mean, so correlation analysis. Again, this is a very good. I'll make this very simple. Correlation by its nature, let me just tell you what correlation is. Correlation by its nature is not causation. It does not mean that when two variables x and y are correlated, then it does not mean one causes the other. Correlation is just movement. Movement. So briefly, two variables are said to be x and y are said to be correlated. Said to be correlated. Sorry, if two variables x and y are correlated, then it does not imply that x affects y or vice versa. That's what causation is, that one affects the other. And there are three types of correlation. There are three types of correlation. Number one is positive correlation. Positive correlation. Two variables x and y are said to be positively correlated if a movement in x is accompanied by a movement in y in the same direction. They move in the same direction. If a movement in x is accompanied by a movement in y, i.e., they are moving in the same direction. For example, why do farms advertise anyway? Farms normally advertise based on the knowledge that the more you invest in advertising, the higher ought to be the sales volume. So if advertisement cost is X, sales volume is Y, then of course we know that the higher the investment in advertisement, the higher should be the sales volume. Otherwise, farms will not have any incentive to advertise. Number two, negative correlation. Two variables are said to be negatively correlated. Two variables, X and Y, are said to be negatively correlated if they move in opposite directions. That's a movement, an increase in X is accompanied by a decrease in Y, and vice versa. An increase in X is accompanied by an increase in Y, and vice versa. So there must be two variables. Of course, you can have more than two variable correlation, but here we will deal with two. For example, the example I have here is fuel consumption efficiency of vehicles and their weight. We know for a fact, and engineers will tell you, that the heavier the vehicle, fuel consumption and efficiency, the heavier the vehicle, the lower the efficiency. Lorries are less efficient than cars. The heavier the vehicle, the lower the fuel consumption. Incidentally, that's why they use this most. Otherwise, if they're using petrol, they would know what to do. So those are negatively correlated. And there are a number. You can cite many examples in business or in any other sector of variables that are positively correlated or negatively correlated. And you can research business application. So that is positive correlation. Then lastly, the third type of correlation is null, N-U-L-L, or spurious. Spurious is just spurious. It's like this. Spurious. 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 Spurious just zero anyway. Zero correlation. Spurious correlation. Two variables are said to be spuriously correlated if X and Y are said to be spuriously correlated if they have no relationship. No relationship. And this is one of the most important types of correlation in predictive statistics. This one of the most important, in fact, if not the most, in predictive statistics. But all of them have their value. For example, these guys these people who keep let me just give an example. These people if you're from Narok, you know, they have a tendency of keeping bulls and cows. So you go to a household. I'm just giving you a rudimentary example. You go to a household, then you look for you ask the head of the household their age. So the kid will tell you, me, I'm 40. Then you again ask about the age of your bull, your oldest bull. They'll give you the age of their oldest bull. Then you cannot say that the older the head of the household, the older the eldest bull, the oldest bull. You cannot. It's like you're comparing goats and crocodiles. There is no relationship. But that is that you can also look at actual examples of variables that would be spuriously correlated. And this correlation is on average. On average, look at this on average. How do we measure correlation? So there are two ways of measuring correlation. To check whether they are positively correlated, negatively correlated, or spuriously correlated. Two ways. Sorry, measuring correlation. So you measure correlation in terms of direction. That is one. And number two, in terms of the strength of correlation. Direction and strength. So there are two ways of measuring the correlation in terms of those two parameters. Number one is to use what is called a scatter plot. A scatter plot. I showed you scatter plots where you can draw them. A scatter plot. Scatter plots are here. We just use this now. We don't waste time. Scatter plots are here. So this is a scatter plot. You see the Y on the x-axis, x horizontal axis. You don't join these points with a line or a curve. You just scatter them in a graph. The above is positive correlation. The lower one is a negative correlation. The above positive, the one negative. The right-hand side is not your baby. The rest of it is curvilinear. We can change the non-linear to linear by taking logarithm, but we're not going to go there. You just concentrate on the left, linear relationship. So this is strong. So you can have strongly positively correlated, which is on the left, up there, or weakly positively correlated. The lower one, strongly negatively correlated and weakly negatively correlated on the right. So you can measure strength. So a scatter plot can only give you, of course it will give you the type of correlation, positive or negative, but it only gives you the perceived strength. You can only say that it is strongly positively correlated or weakly, but there's no value. So that's what it does. It gives you perceived strength. How about spurious correlation? No relationship. When your scatter plots are going like a circle, or when you plot them, it's like a horizontal line, or when you plot them like a vertical line, that illustrates, you just plot your data, you know these are spuriously correlated. Then you can check where they're spuriously correlated. So that's one way. You use a scatter plot to measure the actual type, but with the perceived magnitude. Perceived magnitude. Method two is to use what is called correlation coefficients. Correlation coefficients. This will give you both the type of correlation and the actual magnitude. The type of correlation and the actual magnitude. Yes, Karimi. Or your hand is raised by mistake.
So that's under, yes, it's raised. I'm saying that is under what?
You know, we are
the direction.
But I'm sharing things here. So are you on what are you
I'm
checking?
just your screen is showing.
Oh, what's my screen showing actually?
So
it's
are we
showing
setting
no
another
correlation.
What's my screen showing? I want to know.
No correlation.
Yeah. Which is
your
under
screen
which,
is showing the
under which
scatter
measurement
plot
type?
with no correlation.
It's under what?
The direction of correlation.
Which is under which what? Which topic there?
Spurious
The
correlation.
ways of measuring correlation.
Ways of measuring correlation. I'm going to the second one. The second way of measuring correlation, which is using coefficient of correlation. Coefficient of correlation. That is the best. But of course, again, you will always draw scatter plots. So here, we have two coefficients of correlation. Two coefficients of correlation. That will give you both the type and the actual magnitude. Number one is called Karl Pearson's. Karl is here. Karl Pearson is a Russian. He's a Russian mathematician. Karl Pearson's correlation coefficient R. Letter R, don't use your own symbol, letter R. When you see R in this context, we know you're talking about Karl Pearson's correlation coefficient. In some textbooks, it's just called correlation coefficient, but we want to differentiate because there are others. This R is appropriate when the level of measurement normally is of ratio type. Ratio type or ordinal. Then the next one is called Charles-Spearman rank, correlation, coefficient, rho. That's a Greek letter rho. But it is normally used when the level of measurement is ordinal. Rank is order, ordinal. So if you have data you have collected, which is not ordinal, you must change it to ordinal before you use Charles-Spearman's. The current version of SPSS has both Karl Pearson's and Charles-Spearman's. The lower ones do not have. What are the features of these correlations coefficients? Number one is that they're unit free. You can compare, you can compare sales volume and advertisement cost. Sales volume could be number of units, advertisement cost would be in Kenya shilling, unit free. Number two, they range between -1 and +1. They range both of them range between -1 and +1. So this is the critical thing about this feature. Number one, when R and rho is equal to +1, then the two variables are said to be perfectly, positively correlated. If you were to draw the scatter plot, they would lie on a straight line. Perfectly, positively correlated. And when R and rho are between 0 and 1, between 0 and 1, of course excluding 0, then the two variables will be said to be positively correlated, but with different strengths. For example, the closer the R and rho to 1, the stronger the positive correlation. The closer they are to 1, the stronger they are, the stronger the positive correlation. While the closer they are to 0, the weaker the positive correlation. But when they are equal to 0.5, then that is moderate, positive correlated, 0.5. So below 0.5, weak. Above 0.5, strong. Similarly, when R and rho are equal to -1, then the two variables should be said to be perfectly negatively correlated. Their scatter plots will be on a straight line. And when it's equal to 0.5, moderate. Below 0.5, weak, -0.5, weak. Positive 0, negative, beyond -0.5, strong. Strongly negative. Now lastly, when R and rho are equal to 0, then the two variables will be said to be spuriously correlated. Spuriously correlated. So that's what spurious, either of them, either R or rho, it doesn't matter. So this is what I'm trying to say here. Scatter plots. Of course, forget about the line. That line there is the regression line, which I'm not bothered about here. Just look at the plot without the lines. +1, -1, +4, -0.5, 0. Spurious. So let's briefly introduce then Karl Pearson's. Karl Pearson's correlation coefficient R. Karl Pearson's correlation coefficient R. It is driven by a model, just like all the others we have done, mathematical model. So the mathematical model for Karl Pearson is this one. I encourage that you get used to the lower one. The lower one is what SPSS also uses. That's also what Excel uses. That's what most computer applications use, the algebraic equivalent of Carl Pearson's. So this is what we want to calculate. N is the sample size. X is one of the variables. Y is the other. So X could be sales volume, Y could be advertisement cost. So I will go and show you how to determine R here. How to determine R using this one here, which is our Carl Pearson's. To do that, I go to SPS, to Excel. You go to Excel, Microsoft, come here. So we are in Excel. We are calculating R, Carl Pearson's correlation coefficient R, which is here. Always change this thing. Suppose that a firm wants to check whether there is a relationship between the advertisement cost X. That's the advertisement cost. Let me write it here. X on sales volume Y over the last 1 year. So these are years. These are months. The months of course start from a month. Months of course start from 1 to 12 plus 1, 12 months. Then advertisement cost in thousands of Kenya shillings. I just do a random number generator, run between, say, this and millions of Kenya shillings. This is say 4 to 10 million. Okay. Run between to 10. Then I do the same here. You can just use the same, it doesn't matter. Run between 8 to 10 also. And I generate random numbers here. These are the sales volumes with corresponding advertisement costs in millions of Kenya shillings. Or even this one here, the other one here can just be sales volume in units. It doesn't matter because it's unit free. This one here. So this, we want to get R and check whether the two variables are correlated so that they can continue investing in what? In advertisements. If it's negative, then they don't have to. There's no relationship. There's no need spending millions of Kenya shillings advertising when your sales volume will come down. So what do? Use what I've been, convert this relationship here into a table. This table tells you that N we know 12 months. They are here. XY means that you require a column here called XY for each month. XY for each month. And I do it for all of the months. Then of course I'll sum. We also need sigma X and sigma Y and sigma XY. So I can sum all these. They are here. Because I'm using Excel. I can sum them because we
Is
require
that
the sum.
XY?
Eh?
The XY.
Pardon?
XY is not
The values for XY.
XY is 9.
This is not right, eh?
Yeah.
This one, times that, This one here times. This one here times
10.
times 10. That one, That's the value which will come here like that. Those are the products, Then you sum them. So this one here is sigma XY. This one here is sigma X. This sigma Y. This sigma XY. But this model also tells you require X squared. It is here. X squared, which will sum for each month. So I also need X squared.
But
Please, can you
everything
mute,
else must be.
Can you mute, please?
Everything else. The plain black t-shirt, the plain.
Excuse me? Can you mute? Or I remove you?
Alice.
I'm sorry.
So let's get x squared. X squared is this column here. Squared. And for each month, then you sum them. So we get x squared here. But you also need y squared. It is here. It is here. Here. Y squared. The rest are summation. So we also have y squared here. Y squared. And y squared is just this. That one. For all this. Then you sum. We sum. So this is sigma x squared. This is sigma y squared. And you have all the information you require to calculate R. To calculate R. Those ones. Then you substitute here. And this is what I want you to write, because I'll send you this. You substitute now. And please write it. R is equal to what? 12 times. 12 times what? 12 times xy is what? 518. 12 times 518 minus 72 times 84. That's sigma x times sigma y, yeah? This is right. I know why I'm telling you to do this. Divide by the square root. Square root. You must use this. Use this bracket here. This square bracket. You'll know why. The square root of 8 times sigma x squared. Sigma x squared is 470.
8 or 12?
12, sorry. 12 times sigma x squared, which is 470, yeah? Minus, this is my question now. What is this? What is it? What are you putting here? Squared.
72
72 squared. Then bracket. Again bracket. Well, these brackets are here. So again, large bracket. You are going to multiply this by 12 times sigma y squared, which is 632, 638, eh? Minus what?
84 squared.
84 squared. So this is what I'm going to do. I'll start off with, I'll do it carefully. If you do that substitution, remember this one here, you're going to do this, you multiply the two, then get the square root, eh? So the numerator, our n is 8. Let me just do this. Let me get the numerator. But you have put the numerator is up here. I'll calculate for you. Which basically is 8.
No, 12.
12.
Times, sorry, 12, sorry. 12
Yeah.
times what?
518.
518. Bracket.
Minus.
Sorry, minus.
No.
72.
72.
Times 84.
Times 84. That's our numerator, 168. 168, eh?
Yeah.
Denominator, we get the first term. I just call it term 1 here, because you have substituted, eh? Term 1 to me is this one here. This one, the x one, this one, eh? The first part, eh? Which is 12?
Will be 12.
12 times what?
470.
470 minus what?
72 squared.
72 squared. Whole squared. That's the first term. Second term for the y, the one for the y, eh? Second term
That
is
is
what?
x.
Second term I put equal sign. What is it? 12?
12.
Times?
638.
638.
What?
Minus 84 squared.
84 whole squared. That is term 2. So what do you do with these two things? This one?
You multiply.
You multiply.
Good.
After multiplying, what do you do?
Square root.
Weird. I'm going to do it here. So this times that bracket whole square root 0.5. 523. What do you do with this one here? And this one? This is the denominator.
Divide.
Divide them. So therefore, R is equal to this divided by that. 0.32. Which one is positive? So X and Y are positively correlated, are weakly positively correlated. Why? Because this is below 0.5.
0.5, yeah.
Weakly positively correlated. Am I clear there, please?
Yeah.
Yes.
Now, if you had more than two variables, you must do them in pairs. If you had X, Y, Z, you must check relation between X and Y, X and Z, Y and Z. Because there are two by variable, by. So this is positively correlated but weakly. Which result I can get from Excel, and I can also get it from SPSS. But from Excel, you get it from here. From Excel, you get it from data analysis toolpack. Data analysis toolpack is here. Correlation is here. That's correlation. Then it tells you to define the input range. Input range are everything, including their labels up there, X, Y. Then you instruct Excel that the first row here, X and Y are just labels anyway. They're just labels. Then you tell it to new sheet, new worksheet, new workbook, whatever. You can just run this. It doesn't matter. Then I'll share. I'll share because it disappears when it calculates it. Right? I'll share what you have gotten from Excel. And we got 0.321. It is here, 0.321. That is Carl Pearson correlation coefficient. Correlation coefficient, a very important measure of correlation, which is here. I'll go back now. I think that's the other one we'll deal with the next, but the last one is here. So I don't want to be. I come and share this. Come and share this. This one. And this is it. So here, I had an example here for you, which also is solved example. This is this of course is vehicle type, weight of the vehicle, and highway fuel consumption. Of course, those are the figures. Determine the correlation of X, R, and interpret in terms of direction and strength. Does this confirm conclusion for scatter plot? Oh good. No. I'll go back. Here. This result here we have gotten should be consistent with what you get from a scatter plot. Where is the data? Where is our data? This one. So I can do a scatter plot here. A scatter plot. Insert. Scatter. The simplest scatter plot is this one. Scatter plot.
Prof, I'm not
You
sure
can
if it's on
see your
only, but you
screen.
can't see your screen.
I'll just share again. Now moving from screen to screen. I'll share again. Excel. Come here. Come here. So to do a scatter plot, you select your range. It is there. Then I go to insert. Scatter plot. Scatter plot is here. Pick the simplest scatter plot, is this one. This is our scatter plot. What about this one? Forget about it. But of course, this is X, that is Y. X and Y. Then you see this one here, they are far away. This is why 0.32 weekly. If they were perfect, then they should have been on a straight line, this plot here. So that 0.32 confirms what we got with the conclusions we have drawn from the scatter plot. That's what that question was answered asking. There. I'll go back there. Go back there. Correlation. This is it. So this is it. So I came here, calculated, and this is the scatter plot for this one here, which says just negatively correlated for this data. Then of course I used the whatever the algebraic method, but you can still use the other method. I did use the algebraic method. I used the first one here. I use this one here, but I want to use the algebraic equivalent, this one. Because this one is important. This is used to do other things. You can go and calculate this data now, not using this, but using this, and check whether you get the same result. That will even be better for you. But I've given them to you here. You can check. Here, R was negative 0.894, 0.898, which is strongly negatively correlated. Which same value we should get if you use the algebraic method, the algebraic equivalent, which I have up there. This one, the lower one, to get the same thing. So please forget about this. So this is next week. Charles Piermans, next week. Clear? Done. So we will deal with Charles Piermans, then regression, and that will be it. So we'll just stop there for today.
Excuse me, sir. On Excel, I can't find the correlation under data. Under phone, you said under.
No, we are here. You know, you cannot find that under data. You go to data here.
I went.
Did you get? Have you uploaded this? This one? Do you have
Yes.
this?
Yes.
So, but if you have it, then you have this.
No, I don't have that. Sorry, I think my Excel is a different version.
No, you cannot be a different version, sure.
The template, you need to map that data analysis.
So you need to check, but how did you get it?
Like, just go back to data.
How did you activate data analysis?
I haven't activated it.
That is it. So go to File, Options, then get Data Analysis Toolpack.
Okay.
File, Options, get Data Analysis Toolpack. The same way we did. Already, I thought I showed you how to do this.
Yes.
Yeah, because if you have not, then you can't have it. So you go to File, Data Analysis Options, then get this. Then now you'll get this one here. All these possibilities. That's the only way you'll get it there. So we stop,
Okay.
Stop,
Yes.